Welcome to 8.4 video 2. Did you know that Unit 3 and 8 have the highest weighting amongst the multiple choice section on the AP exam? And Unit 8 is widely considered to be the most challenging unit. Well, I've got a secret. Understanding the majority of what goes on in Unit 8 comes down to 8.4. That's why my first videos are starting with this topic. I'm going to show you at the particle level exactly how weak acids and bases react with their strong counterparts. I'm going to teach you how to filter out some of the noise associated with these questions and focus in on how to think through solving these problems. This topic's a tough one, but it's about to get a whole lot easier. First, I want to do a quick review of strong acids so we can talk about why they're different than the weak ones. HCl is a strong acid, which means that it completely dissociates in solution. At the same time, the conjugate base, that chloride ion, is just a spectator. We don't care about that. That really simplifies the way strong acids behave in solution. Weak acids are different. HF is a weak acid, which means it does not fully dissolve. It's only partially soluble. If I dump this into solution, I'm gonna see them stick together. F- is the conjugate base to the HF. We left out the conjugate base to HCl because it was just a spectator. Unfortunately, with weak acids, their conjugate bases do affect the pH of a solution. The conjugate base to a weak acid is a weak base, and it will impact the pH. This is not a spectator. We can't just take it out of the chemical equation. So what does that look like? I'm going to use HA as my generic form for a weak acid. We'll see as we work some other problems how A can turn into a lot of other different substances. But this is my weak acid. We take this, we dump it into solution. It is comprised of H plus and A- stuck together. We're going to add to this solution the strong base. Now notice this is just OH- in the chemical equation because the cation for strong bases gets removed. This could be NaOH, KOH, LiOH, anything. We ignore those because the cation is a spectator. I want to bring back something from topic 8.1 because we dealt with the autoionization of water, and the Kw for this split of H plus and OH- was incredibly small. This reaction is heavily reactant favored. What that means is that hydrogen ions and hydroxide ions really like to stick together. This is going to be indicative in solution. H plus and A- isn't going to break apart. But now as I put this hydroxide ion into solution, it is going to have a much stronger attraction to that hydrogen ion than the A-. So anytime I have excess hydroxide, it's going to attract that. What do we get when H plus and OH- go together? We get water. To write the net ionic equation, I've got my weak acid and my strong base already in the reactants. So my products are going to be comprised of that A- and the H2O. A- is the conjugate base to the weak acid HA. H2O, of course, is water. It's a liquid. We can just leave that there. This is the net ionic equation for the combination of a weak acid, the generic form HA here, and a strong base. Strong base is always going to be the OH-. So the only thing that's changing in here is the identity of whatever substance A is. To give you a few examples of this, hypobromic acid, HBRO, reacting with any strong base. Another very common one is acetic acid. That carboxyl, the COOH, is one of the most commonly used weak acids. So make sure you recognize it and its conjugate base, COO-, the carboxylate ion. Before I get into the mathematics here, I'm only showing you this ice table because I want to give you these numbers to show you how this is all going together. To be honest, I don't think any of the problems involving buffers are really going to use ice tables. All right, I'll show you those later on, but for now, this is just an example so I can show you the function of what's changing. In my solution, I've got pure HF. Notice that all of these are intact because HF is a weak acid. When I take that hydroxide ion and I throw it into solution, its attraction to this hydrogen ion, remember, is based upon Kw. Very small value, hydrogen and hydroxide, they like to stick, and they form water. In the ice table, we took out one HF and one OH-. This is a limiting reactant problem, and it's leaving me with one F-, in solution and 3 representations of HF. If you didn't notice, the water disappeared here because the whole solution's in water, so we don't really need to pay attention to that. Typically, we leave water out because it just kind of takes up space. At the beginning of this, I had everything as HF. Now I have HF, the weak acid, and F minus, its conjugate base, both present in a reasonable concentration. They're both there in solution. This is a buffer solution. A buffer is a solution that has a reasonable concentration of the conjugate acid-base pair. What is exactly a reasonable concentration? You don't need to worry about that. We're not going to try and trick you with, oh, it's just this much. But when you have 25%, 1 out of 4 representations being the conjugate base, that is a reasonable concentration. This is a buffer solution. What happens if I take and I throw in another hydroxide ion? That's also going to stick to another hydrogen ion and make water, which again, we can phase out because we don't really care about that. At this point, I've consumed half of the HF. Notice that it went from 4 to 2. Half of it has been converted over into the conjugate base. This is what's known as an ideal buffer. An ideal buffer is a solution that has an equal concentration of that conjugate acid-base pair. Notice, HF, 2 moles. F minus, 2 moles. I have the same number of moles in the same solution, right? Same solution, same volume. So that means I have the same concentration of both of these. A buffer solution has equal concentrations of this conjugate acid-base pair. To quickly review that, we started out with the HF solution. 4 representations, call it 4 moles. If I put in half as much strong base, 2 representations of OH minus, they're going to react with the hydrogen ions, form water, and then we don't really care about them. This now gives me my equal concentration of HF and F minus present in solution. This is how we created an ideal buffer. An example question. Whenever I put one of these up, feel free to pause the video, dive in, see if you can figure it out. Part A says write the net ionic equation for the combination of these two. Whenever you're looking through a question, you need to hone in on the specific information required to answer that question. So I typically like to jump to the question first and then look and see if there's extra things in there. Write the net ionic equation for HiO2 and KOH. So we don't even need to read the information provided above. We have everything we need right here. HiO2, this should be, it's got the H in the front. You should recognize this as a weak acid. Typically speaking, I might provide a Ka along with this just to give you a hint that it's a weak acid. But since it's a weak acid, we have to write the whole thing. There's no spectators involved in this. We write it all. The KOH is the strong base we're adding into this. Strong bases are just OH minus in the net ionic equation. For the products, the HiO2 is going to lose that H plus. When it comes off, we take off the H, we get IO2, but it's an H plus. So we're going to drop the charge by 1, giving us IO2 minus. Make sure you're comfortable in writing these chemical equations. A lot of times they'll be given to you in the question, but understanding their function is really going to help you move along. Now, the H plus that came off of that stuck to the hydroxide. Hydrogen and hydroxide gives us water. Next part, create an ideal buffer from these two solutions. So when I'm mixing two solutions together, the first thing you want to focus on is what are their concentrations? We got 0.5 molar of the weak acid and 0.25 molar KOH. Notice 2 to 1. This is really common to eliminate most of the heavy mathematics. This is a chemistry test. What you need to display is that you understand the concepts, not that you can spend 4 hours doing calculations. So this set ratio, 2 to 1, is really, really common in these types of questions. We established to create this buffer, we need half as many moles of KOH as we do HiO2. Don't worry about the calculations. Think about it. If the concentration is half for the strong base, that means for every milliliter of each we mix together, we're getting half as many moles of KOH as we have HiO2. If I want to put in half as many moles of KOH, I need the same volume of both of these two solutions. The volume in the problem was 100 milliliters of HiO2, so we need 100 milliliters of KOH to go with it. Whenever a question is followed up with a justify your answer, you want to make sure the first thing you do is answer that question. Then you can provide your justification. So I've got 100 milliliters of KOH. There's my answer. Next, your justification shouldn't be your thought process. Feel free to write that down, put whatever you want together, but your justification should be specific to the question that is asked. This question is about creating a buffer by converting the weak acid into the conjugate base. My answer addresses that. This volume will convert half the weak acid into the conjugate base, put together in a very nice specific manner. This is not the only acceptable answer for this, but this is the way to create a very short, specific answer that can be utilized on the AP exam. Question 2 is similar to question 1 in that we need to write the net ionic equation. This time, you've got NH3. NH3 is an amine group. Being a weak base goes fully into the equation. HNO3 is a strong acid. A strong acid is only written in a net ionic equation as an H+. Bases are proton acceptors, so that NH3 is going to attract the H+. They're going to wind up sticking together to form NH4+. This is a very, very common weak base reaction. For the second part, we're looking to create that ideal buffer again. When you want to create a buffer, start by looking at the concentrations. What do we have? Both of these are 0.1 molar. Okay, same concentration. Now keep in mind, just like the previous problem, we have a certain amount of NH3. We want to add half as much strong acid to that. If my concentrations are the same, I'm getting the same amount per milliliter, so that means I'm going to need to add half the volume. The volume in this problem is 50 milliliters, so half of that would be 25 milliliters of HNO3. My justification for this is in relationship to what happened in the problem. This is the volume of HNO3 that'll convert half of my weak base over to the conjugate acid. This covers the first method of creating a buffer. I kind of refer to this as adding the strong opposite. If I'm creating a weak acid buffer, I want to add strong base to it. If I'm creating a weak base buffer, I want to add strong acid to it. To quickly review the first method in dealing with a base. All right, here's my NH3, the problem I had a moment ago. Let's assume I've got 4 representations. When we create this buffer by adding in the strong opposite, we want half as much because we're converting it into the conjugate. So we drop in half as much H+, they group up with the NH3s, they wind up becoming NH4+, and now I have 2 representations of each, the weak base, NH3, and its conjugate acid, NH4+. That's my ideal buffer. This is only one method of creating a buffer. There's also another way to go about this, and that's adding a salt containing the conjugate. Let me give you an example. Let's take NH4NO3. Notice, because of that NO3 anion, it's going to fully dissolve in water. That's why this has a forward arrow. The NH4NO3 is made of these 2 particles. They're going to split apart in water. Now, the NO3 is a spectator ion, so we can ignore that. What this means is that NH4NO3, when dissolved in solution, effectively produces NH4+, the conjugate acid to the NH3. That's what a salt containing the conjugate does, is it fully dissolves, giving you nothing but the conjugate and a spectator. So we dump this over there. What happens when we put that in solution? It doesn't interact with anything. It just directly adds into the solution itself. This isn't the first method with the strong opposite where we're converting it into the conjugate. Adding a salt containing the conjugate just directly adds it to solution. How many of these do I need? I need 4. There's my 4 representations. Now I've created an ideal buffer. So notice this is a little different too. We're not adding in half as much because we're not converting it to the conjugate. I need to add just as many moles of the salt containing the conjugate as I had the weak base to start with. There's Two different things depending upon what we're starting with. If I've got a weak acid buffer, I want my salt to contain the conjugate base. If I have a weak base buffer, I want the salt to contain the conjugate acid. In terms of creating an ideal buffer, these are made two different ways. So my weak-strong combination is going to be in a 2-to-1 molar ratio because here I'm converting the weak substance into the conjugate. When I add the salt containing the conjugate, I want these in a 1-to-1 ratio because I'm just adding it directly into solution. Question 3. Try and find out what you need to hone in on in order to answer the question. All right, this one, I didn't even try and add in extra information to confuse you. We know that happens sometimes. So let me actually filter out everything that we don't need. We got this data table with 4 different solutions. Right away, I noticed that the concentration of everything here is exactly the same. That simplifies some of our aspects. The question is asking, first, which of these substances in the data table can we add to that HCOOH? What is HCOOH? It's got a carboxyl group. That is a weak acid, specifically an ideal one. When you work through any buffer problem, what I would highly recommend is always first identify the conjugate acid-base pairs. We've got the weak acid, HCOOH. The conjugate base to this is HCOO-. You should be comfortable with those carboxyls. Which one of these can we add to a weak acid to create a buffer solution? Let's identify what they are and see if mixing them together will work. HCl is a strong acid. If I mix a weak acid and a strong acid, I get an acidic solution. Not a buffer. No, HCl is out. NaCl, that's table salt. That's not going to do anything. It's a salt, but it's not containing the conjugate. This is a distractor. We can completely ignore this. This is not going to create a buffer solution. Next one is KOH. Strong base. Yes, if I take a weak acid and I add a strong base to it, that will create a buffer solution. The next looks like Hakuna. HCO. Hey, that looks a whole lot like the conjugate. Usually the cation is on the front of the chemical formula, but since the H is coming off the end of the carboxyl group, they typically put the cation, could be an Na, could be a K, could be an NH4, they put them on the end. So this is a salt containing the conjugate. That means we could also use this one to create my buffer solution. Second part, how much of these do I need to create an ideal buffer? First, dealing with the KOH. Let's say that we have 2 representations of weak acid. If I'm adding in the strong base, that's the one that converts the weak acid into the conjugate base. So I only want half as much, because when that hydroxide comes in, it's going to pull off the hydrogen ion, forming water and the conjugate base. All of the concentrations are the same. If I want half as much KOH, I need half the volume. The volume of the original weak acid was 25 milliliters. Half of that is going to be 12.5 milliliters. That's how much KOH I need. Now for the conjugate salt, this one works differently. So let's start over. I've got 2 representations of the weak acid itself. I'm not converting those into the conjugate base. I'm just dumping in the conjugate base. So I need 2 of those too. That's equal amounts of the weak acid and the conjugate base together. So if they have the same concentration, I need the same volume. The volume was 25 milliliters, so I need 25 milliliters of the HCOONA in solution to make an ideal buffer. Here they are, the methods of creating a buffer, just to review. When you've got a weak acid or base, if you're adding the strong opposite, you're converting it over. So you need half as much to create that ideal buffer. If you're adding the conjugate salt into solution, you're not changing it. You're just adding in the same amount to make an ideal buffer. Make sure you're familiar with these. And notice the example questions that I ran through, they didn't have any heavy calculations. A lot of them relied on a set ratio to make sure that it was easy to sort through and figure out what you needed. That's the end of the material for 8.4, but stick with me for another 30 seconds. If you hadn't noticed, I'm new to YouTube. If you're watching this, you're investing time and money into taking a test sometime in the spring, and I'd like to help. I plan to grow this channel into a resource that helps students just like you. If you learned something while watching this video, please hit the subscribe button. It's free for you, and it'll help me to generate more content like this and to improve my videos. Let's help each other out. You hit the button, and I'll do tons of work to make life easier for students just like you. Thanks for watching, and please, keep coming back.